Gulab Shah, you may start the meeting.
Welcome back everyone to the last session of ICDA 2020. In this session, there will be one invited talk and 5 contributory talks. I request Dr. S. Senorita Devi to chair this session, and before that, I request Dr. Himadri Shekhar Das to give an introduction about the invited speaker of this session. Sir.
Yeah, thank you very much. We now invite Shashi Kiran Ganesh from the Physical Research Laboratory, Ahmedabad. So he is a scientist in the Astronomy and Astrophysics Division of Physical Research Laboratory, Ahmedabad. He joined PRL in 1995 after his master's in physics from Gujarat University. He completed his PhD at PRL on the multi-wavelength studies of the Milky Way galaxy. He is interested in astronomical instrumentation and is PI for a multi-function near-infrared measurement for multi-function near-infrared instrument for PRL's upcoming 2.5 meter telescope. He has a good number of publications as well as conference proceedings. So I invite Dr. Shashi Kiran Ganesh in this session. Over to Senorita Madam.
Good afternoon, everybody. So right now in this last technical session number 4 for this conference, first of all, in this session, we have an invited talk on recent observations of astrophysical dust by Dr. Shashi Kiran Ganesh from Physical Research Laboratory, and Sir Himadri, he has already given a very nice introduction for him. So may I request Dr. Shashi Kiran Ganesh to please come forward and give the talk. And sir, for your information, there is 45 minutes for the talk and some 15 minutes for the discussion time. Sir, please.
Okay, thank you. I'll just start the presentation. One moment. So am I audible? Heard?
Yes, sir, it's quite
okay.
audible.
And the screen is fine, right?
Yes, everything is fine, please.
Thank you so much. And thank you to Professor Das and his team at Assam University for organizing such a wonderful conference, and also to invite me to give a talk. I really did not expect to have such a billing, and so what I'm planning to do is to cover observational aspects of astrophysical dust. So the title, although it said recent observations, I shall be focusing on a very biased view of astrophysical dust, in the sense that these are observations and results which I have been associated with to some extent. So it's a very biased and personal view in that sense. And definitely there will be results which have come in recent times, which probably have updated further and then done much better progress in this subject. So those who are interested should go further and look beyond what I shall be talking about. Much of it will be hopefully at an introductory level, because I'm seeing that a lot of students are here. And so mostly I shall go around like this. I will talk initially about conetary dust, and then a little bit about how we can observe it using different techniques. Also regarding circumstellar and interstellar dust, what are the signatures that one can use to study these different manifestations of dust, okay? And as I said, this is not a complete review of the subject. Obviously, it's not possible to do that. You'll need a whole conference on it, but hopefully I'll try to do some justice in the 45 minutes allotted to me. So to start with, since there are many students and hopefully in future they may consider to come to PRL also. So these are the telescopes which are available at Mount Abu Observatory, and At the center, of course, is the 1.2 meter telescope, which is currently the workhorse of the astronomy division. We have a 50 centimeter telescope, which is being used for cometary studies as well as for variability of a wide-ranging set of sources. And also a 43 centimeter, again for variability studies, mainly for exoplanet transits. And then a new 2.5 meter telescope is coming up. This is a picture from late last year when we were able to go there. After that, there has been a lot of progress in the construction, of course, but due to the lockdown, we are not able to visit immediately. So the instruments available are optical and NIR polarimeters, near infrared polarimeters up to 2.5 micron, 2.3 to 2.5. And we also have imagers and spectrographs covering the optical and near infrared wavelength range. Okay. So if in between, if there's any questions, please feel free to ask. It would be nice to have an interaction so that we know that I'm not cut off from the thing. Okay, so optical polarimetry at PRL is mostly using this optical polarimeter, which is mounted the Cassegrain focus of the 1.2 meter telescope. Professor Ashok Sen is one of the early pioneers on this instrument. He has used this instrument for comet observations quite extensively, both from here as well as from Kavalur, I believe. And since '94, this instrument has been used exclusively at the 1.2 meter telescope. Earlier, they used to take it to Kavalur. That's the IIA observatory. This is a view of the telescope building from outside. Now, of course, we have the 2.5 sitting at the back of this. The other instrument which I would like to highlight is the very compact Shellac instruments LISA spectrograph. It is an optical wavelength range spectrograph covering up to a resolution of 1000. So even for faint comets, we can use it. And it can be mounted at the Cassegrain focus of both the 1.2 meter as well as the CDK 50 centimeter telescope. And this is Kumar standing next to the instrument and next to the telescope. He's standing on a ladder here. So just for scale, just to get an idea of the size of these telescopes. These are pretty small by international standards. This is another view of the instrument. And we have studied a large number of comets so far, and this is an incomplete list. At least half a dozen more comets we have been successful in observing in recent times. Some of the initial ones are objects which Professor Sen had observed. For example, this 1989 Austin and 1P Halley. I think in Austin's case, he had some very successful imaging polarimetry done. So I will not, of course, be able to go through this entire list. I will highlight a few of them. You already heard some results on Borisov in the morning from Arvind's talk. So we'll go ahead further. This background image is one of the latest comets which we have been successfully able to observe. Its background image is from Hanle, and it is by one of the engineers stationed over there. So why study comets? Comets are pristine remnants from the formation of the solar system. And most of the time they are at far off distances. They become active when they move closer to the sun. And you start seeing a dust and ion tail, as you saw in the previous image. This is the ion tail and this is the dust tail. And the why we consider them to be remnants, we shall discuss in a little time, just immediately after we complete this work. And these are usually studied using all the techniques which are available to an astronomer, that is ranging from imaging to polarimetry, okay, through spectroscopy. So what do comets look like? So normally we tell that a comet has a tail which is always pointing away from the sun. And, oh, it's okay. So this is comet Hakutake, as it appeared in the field of view of comet of the SOHO instrument on with the LASCO coronagraph. And I will just want to highlight that as it is approaching the sun and at perihelion, you can see that the dust is still following the trail of the orbit, but the ion tail excuse me, I'll just, yeah. So if you focus on the ion tail, it is always pointing away from the sun, okay? So this is one example where you can actually see the tail and both the tails in the field of view of this coronagraph. In another case where it was the Great Christmas Comet of 2011, W3 Lovejoy. So this is a very spectacular comet. Later on, in fact, it survived the closed pass of perihelion and again regrew its tail. You can see that in the initial stage, you have the dust and ion tails. And as it rounds the sun, the tail has disappeared. It disconnected at the point where the comet was closest to the sun. And eventually you can see that it's regrowing the dust tail here and the ion tail as well. Okay, so these are some examples of what comets look like as they round the sun. So how do we study them? Usually, like you have already heard a lot of talks on this topic, including the excellent review by Professor Zubko yesterday about polarization studies of comets and especially the modeling aspects of it. So polarimetry provides insight into the physical characteristics of the dust grains. And the way to study it is by studying the comet over a wide range of phase, wavelength, and use that information to model the refractive index and the dust grain size distribution. The same thing is discussed again. The dust in the cometary coma scatters the sunlight, and the scattered light is polarized. And this polarization one can observe. And these are two things which are in the hand of the observer. We can choose at what time to observe and at what wavelength the observations are carried out. Well, this is a little tricky. It's not exactly in our hand to choose. You need to plan in advance and then also have the possibility of observing at that time. Sometimes you don't get the comet in a favorable location, and so it's whatever observations are possible are always valuable. Okay. Thus, observing polarization at different wavelengths and phase angles allows us to infer the properties of the cometary dust, as you have already heard yesterday. This is a phase curve. So phase angle is the angle between the sun, comet, and the observer. And the polarization is plotted on the y-axis. This is the normal way of representing the observations. Typically, each point here represents one night of observation, unless it happens to be a close flyby of the Earth, in which case you may get a good range of phases observed in one night. But typically these are long period comets and don't approach very close. So then each dot represents one night of observation. So a significant amount of time is required to follow up the objects. So the dark points here are for comet Hale-Bopp, and the open circles are for other comets. And we already heard yesterday from Professor Zubko about how comet Hale-Bopp until recently was one of the largest polarization exhibitors, and only this year it has been joined by the most recent comet, which he covered in very great detail. It was a very interesting talk where he justified the use of even a broadband filter. We will just see how things may get affected. But it seems that if you use a small enough aperture, we should be able to get reasonable measurements even in broadband filters, which is a very, very welcome news for cometary observers. So this is the phase versus wavelength dependence. And so on the top panel, you have the wavelengths which are used for the measurements. So these are normally narrowband filters of 80 angstrom width. And again, these are from comet Hale-Bopp. And for comparison, comet Halley dots are also represented. And it had a much stronger wavelength dependence than comet Halley. And the indication was that it was dominated by small grains, okay, for comet Hale-Bopp. So once you have this kind of observational data available, you can actually go back and do some simulation of the cometary dust. And this was covered in good detail yesterday by Pritish already. And he has made use of the Vikram HPC of PRL. And the characteristics are already mentioned here using the codes which are available in the literature and on the internet. And there's a limit on the number of cores which can be used at a given time. So this is the number that we used. And he came up with very interesting results, which he summarized yesterday. And one more that I would like to share with you is regarding the regarding the simulations for Comet Halley and Hyakutake. And here the difference between the blue and the red curves is the percentage of hierarchical aggregates. And this is, of course, work in progress from Pritish, and hopefully we will have some very exciting results very soon. And of course, the talk from yesterday was quite useful in that sense to take it further, I hope. So once you have this, you can also do spectroscopy, and spectroscopy allows you to infer the characteristics of the object. And one of the results which I would like to talk about is the near-Earth asteroid, potentially hazardous one, which carries the name 2014 JO25. So this had a close flyby of the Earth on 19th and 20th of April in 2017. And using the LISA spectrograph on the 1.2 meter telescope, we were able to follow this object for a sufficiently long period of its history and of its flyby. And why we decided to do spectroscopy rather than polarimetry or imaging of this one is that it is on a very comet-like orbit. And we expected that there may be cometary emissions from it. There were some indications in the literature about that. And what we saw was a surprise, because we did not see any kind of cometary emissions, but what we noticed was that there was a phase bluing of the photometry from this. I'll just show you the spectra. Okay. Yeah, so the spectra are like this. At high phase angle, it is really nearly flat, and then as you go to smaller wavelengths, there's a reddening. Okay, so or in the other way, with increase in phase angles in this direction, you are seeing that there is a phase bluing. Normally, you expect that asteroidal surfaces would show phase reddening. Okay, but in this case, we are seeing this phase bluing, which we consider is an indication that there is a freshly exposed surface on the asteroid, which is responsible for this phase bluing trend. Okay. Next, what we can do is we can actually go and look at the comets, because that is of interest, as we have discussed in the morning session also. So this is a typical view of at the time of observations, when we, so our LISA spectrograph has two CCDs, one to guide the telescope, and the other to actually acquire the spectrum. So the guiding camera is already continuously viewing the slit in a reflection mode. So whatever light doesn't pass through the slit, that is this black line here, gets reflected to this guiding camera. So it's a very convenient technique for tracking objects which are moving at non-sidereal rates, objects like comets and asteroids. So you can actually sit and make real-time corrections to the telescope guiding. And at the end of, so typically this CCD uses exposures of 3 to 5 seconds, whereas this one we would integrate for about an hour or so for some of the fainter comets. Okay, so that's about the longest exposure that we have taken is about 1 hour. So for an hour, you just keep on monitoring that this object remains on the slit, doesn't move away from there. And at the end of the exposure, you get a well-exposed spectrum like this. And you can actually see how the cometary coma has shaped the emission in the various bands. So this is what the Comet Lovejoy showed us, typical C2, C2, C3, Cn. And then NH2, and then also there is an oxygen line coming from the comet, as well as some amount of NH2. And some of the typical broadband filters which people have been using in the literature are shown here. These are also filters called the international, so these were defined at the time of the Hale-Bopp apparition, and we have a set of these which we use for imaging purposes. Typically, once you have this kind of a spectrum, you can estimate the production rates and the dust to gas ratios and the AF rho from the continuum points. I should emphasize here that this spectrum is after the continuum has been removed. So basically the dust contribution in this has been removed and only the molecular emission is shown. Otherwise you have the typical dust scattered light from the sun, which shows a typical G2 type star spectrum. And that has been scaled and removed from these measurements. And once you do the air flow calculations, this is a proxy for the dust production rates and then the dust to the gas production rates ratios as a function of perihelion distance. Already we have had some discussion about this in the morning regarding C2 and C3C and all these production rates and how we use the scaling laws for them. So it's important to keep in mind these aspects while comparing the results from different comets and different observers. Okay. So results from this were published in Kumar's paper in 2016. And typically we are seeing that there is not much of a difference in dust to gas ratio, although there is a, individually you see that the post-perihelion there seems to be more activity. These are some sample spectra from other comets. And this is Lovejoy, which you have seen already. Pan-STARRS was a real surprise again, one of the few rare comets which had a strong collection of ionic emissions rather than the conventional C2, C3 molecular emissions. In fact, even CN is missing to some extent in this. 46P was observed extensively from Mount Abu as well as from Hanle, and the results are in preparation for that, and I shall not discuss that in more detail. Comet 123P was observed, and then this again is a comet which has had many apparitions towards the to perihelion, and so you end up getting almost no molecular emission even when it is very close to the sun. So you can see that you have a large range of objects, cometary spectra, as you look at them in the optical band. Now I said initially that the cometary dust is a good signature to understand or a good proxy of early solar system materials. How do we say that? So we are saying that on the basis, I mean, that has been an inference right from the beginning based on observations and laboratory measurements on meteorite material and all. But the first really conclusive evidence came when the Infrared Space Observatory, it's a ESA mission, looked at a precursor to the Spitzer mission. So this observatory looked at a comet Hale-Bopp and also at a young stellar object. And the observers were quite surprised that there were very strong similarities in the spectra. For example, in the case of the star HD 100546, it's a young stellar object, and it's still sitting in its stellar cloud where it was formed. And they find that it has extremely similar behavior or emissions corresponding to the forsterite olivine material. So this is basically the amorphous silicate, and then this is the crystalline ones, features which are present. So these were observations by Crozier and Volkens et al. Using the Infrared Space Observatory. And further observations by Infrared Space Observatory on other stars showed similar spectra for post-AGB stars. In this case, it was a binary, and also a carbon-rich giant, IRAS 09, whatever. And these are the features which are rather similar to the ones which I showed here. Okay. So these features show that cometary observations are going to be a good proxy for early solar system processes, materials at the time of formation. Another proof for that comes from this series of observations. The first two, topmost two, are observations from which I've already described to you. And the second two are spectra from the Spitzer Space Observatory of comet 9P Temple 1. Okay, so this one is before and after impact by the Deep Impact mission. So Deep Impact was a impactor mission which went and crashed into this comet, and 23 hours before the crash this spectrum was taken, and 23 hours later actually 24 hours later, after 1 hour of the crash, this spectrum showed strong signatures of the similarity of the olivines in this material. So it's clear that 9P Temple 1 exposed fresh material from the inner buried layers when during the crash. Okay. So this shows that, of course, cometary dust is very closely linked to what we would like to call circumstellar or interstellar dust. And these have very strong signatures in the infrared. And let us see how we can use these techniques to study the circumstellar and interstellar dust material. And one of the works in this direction is from the ISOGAL survey. This was a survey with the Infrared Space Observatory at 7 and 15 micron. And this was combined along with a large number of observations at near and mid-infrared wavelengths from other places. This is a view of the color composite of the 7 and 15 micron image of 1 degree by 20 arc minute of this field. This is in this direction tangential to the galactic plane. And it is quite interesting to see how the color magnitude diagram of this field looks like. We divided it into several sections and plotted the color magnitude diagram for different bins, and the bin closest to 0.0 latitude shows this kind of a dependence, while the extreme field at plus 0.5 as well as minus 0.5 shows a dependence like this. So the black dots are mostly red giant stars. The blue are foreground main sequence stars closer to the sun, whereas the black dots are at this kind of distance. So assuming this kind of extinction, this is the solar system, solar neighborhood extinction law. Whereas if you go towards this direction, this is the kind of extinction that you expect based on what we call the red clump method. Okay, red clump. So we assume that we trace this to be the locus of the red clump stars. Excuse me for these dogs here. We have a big problem working from home today. Okay, so the distance covered in this kind of a very close to the galactic plane is 2 to 4 kiloparsec, whereas when you go slightly above or away from the galactic plane, you can probe further deeper. Okay, so this is a direct indication of the extra amount of dust extinction closer to the plane. So how do we look at that? We looked at that using the red clump stars and the red giant isochrones, combination of that, and then estimated the distances and the extinctions. Okay, so this is the kind of behavior we are seeing. So the distance probed becomes shorter and the extinction seen is higher close to the galactic plane, and as you go out, it improves. So going deeper, with deeper photometry, one should be able to improve on this. You would expect that this kind of distance dependence would be better understood now with Gaia being available. Unfortunately, Gaia distances are accurate only till about 4,000 parsec. Beyond this, one has to be very careful in using the Gaia distances. So that is something to be kept in mind, especially when you use the Bayesian distance estimators. Okay. Going further, once you have the distance and the extinction, you can actually correct for the distance and extinction and actually plot the color k minus 15 versus the bolometric magnitude in k. And this is a good indicator of mass loss, k minus 15, because k minus 15 becomes extremely low or close to zero when you have no mass loss, and then as you are negligible mass loss, and then as the mass loss increases, so this is plotted in the top via x-axis as log m dot, and this line corresponds to the red clump line, and this is the tip of the RGB. Okay, so the stars above the tip are the AGB stars, and this you can clearly see a large mass loss in these objects. And then, but what is interesting is that even for the RGB red giant phase, there is significant amount of mass loss. So this is the phase where a lot of dust is actually being thrown out in the circumstellar environment of the star. So in fact, even the red giants are a significant source of dust in the Milky Way. Okay. So covering this aspect, now we come to what we call the infrared dark clouds. So when you look at the Milky Way in the longer wavelengths, you expect to see a much clearer view, and you do indeed see that compared to the optical window. But even at 7 and 15 micron, we see regions where there are dark patches, okay, similar to what you see even more extensively in the optical window. So these infrared dark clouds were first observed with the as a part of the ISOGAL survey, and they were catalogued, and complete fractal and multi-scale wavelet analysis was done to catalog these objects. And this is the initial image, and then the image after clipping the bright point sources, and then after a wavelet analysis of that, you end up getting a structure of dark clouds. So this was cataloged by Hennebel et al. Way back in 2001, and then these have recently been seen at many other wavelengths, also in emission. One example I would like to share here is the galactic nuclear bulge. So the lower panel is the 7 micron image of the galactic nuclear bulge, the color scale behind it, okay, and the top panel is the 450 micron image of cool dust that's around 10 degree Kelvin, which is measured by the scuba instrument on the JCMT. And this has very nicely traced the cool dust in the nuclear bulge of the galaxy. This is the Sagittarius B region, and this is a very famous dark molecular cloud. And what is interesting is that, you know, you can see a very direct correlation between the strong emission in this 450 micron with the absorption seen in the 7 micron image. Okay, and the same way in the Sagittarius B region also you have such indications, and in many places, in fact here also, although it's not as dark, but then you see that there is a good correlation, almost 1-to-1 contour correspondence. Okay. So this shows that even at 7, in the mid infrared, you can have extinction. And in fact, from our measurements using the glimpse survey data, it appears that this corresponds to extinctions higher than 80 magnitudes in the visual. So it is obvious that with this kind of magnitudes, you cannot probe with near infrared data. One has to look at other techniques to map these things. That brings me, okay, there's one more view of the color composites. This is using 850, 450, and 7. These two, the first two are from Scuba, and the 7 micron is from ISOCAM. That's the Infrared Space Observatory camera on the Infrared Space Observatory. So the blue dots are all the photometric measurement contribution from the stars. You do have some warm dust surrounding them in this region close to the center of the Milky Way. The yellow patches are all strong emission features, which you already seen. This is a close-up of this area. Again, at it's a different composite, 850, 15, and 7. Okay, so 15 corresponds to, again, very warm dust. And at 7, and you have some part of it being photospheric and some part being pH and other things. And 850 and 450, of course, mapping the cool dust in absorption, in emission against the stars. Okay. So having done that, we also have been looking at extinction towards the inner bulge. And this is using the red giants and their expected distribution in terms of isochrones. Okay, so typically we can assume that most of the stars, this can be done towards the bulge, where we can assume that most of the stars are at around 8 kiloparsec, and use just the color information, color magnitude information, to estimate only the extinction. There is no need to look at the distance, though there is a differential spread across the bulge. So that kind of work was first done in this by Schultheis and myself and other collaborators. This was published in '99. This was the first large-scale and continuous map of the inner galactic bulge. Before this, there were, in fact, single point photometer measurements of extinction by Catchpole and Glass and other collaborators from South Africa. And this was a giant step forward. Now, of course, people have gone even further ahead and started talking about 3D dust distribution and extinction using both glimpse data as well as theoretical modeling and in fact deeper photometry from various surveys. Okay. So the final step that I would like to discuss for today is our very recent observations with the Mount Abu telescope, 1.2 meter telescope. This is using an instrument which is a near infrared camera with a polarimetric add-on. This instrument was developed, the polarization module was developed and added on in the last couple of years, and it has been used for observing a few molecular clouds. The idea behind using near infrared wavelength is that it would probe the more extincted regions in the molecular cloud compared to the optical, where the optical one would be able to probe only the outer regions of the molecular cloud for interstellar polarization. So the cloud in question is LINS 1340. It's a field in Cassiopeia region. And Kuhn et al. Have been working on this cloud for a very large body of work and over several publications. And they estimate that the distance to this cloud from their work is around 800 parsec. When we compare the J-k magnitude versus the distance from Gaia, we find that their estimate seems to be reasonable because you see a step in the color distribution at exactly the kind of distance where they have indicated as the start of the cloud. The dots here, the small dots are the photometric points with 2 mass, and the colorful points, larger symbols, are for objects for which we were able to cover with the infrared polarimetry. Okay, especially keep track of these squares which are showing increasing color with distance. These are the objects which are very closely associated to the RNO8 core in the molecular cloud. So this is the entire molecular cloud. Some part of it we were able to cover it, and the innermost contours. These contours are from the WISE 4 filter band, and these are the thick stars are the ones which are closely associated to this molecular cloud core, and the polarization measurements are closely aligned. We see that there is a strong dispersion in the rest of the field, but even there we see some predominance of 2 specific directions. What is of interest here is that when you look at the molecular cloud using the WISE images, which basically trace the warm dust in that region, then you see that very close to the cloud core, you have a reasonable overlap in the polarization vectors, and the centralmost star here is a little different in the sense that it has polarization slightly oriented slightly away from the rest of the objects, but at the same time Gaia shows a very discrepant distance for this object. So we have estimated the magnetic field using the Chandrasekhar Fermi method, and we find that if we don't include this star, the dispersion is small and we get about 45 microgauss. And if we include this star, the dispersion increases and you get 18 microgauss as the overall plane of sky magnetic field strength. So this is regarding the L1340 polarization method. We are in the process to now extend further in this for different directions, different molecular clouds, and hopefully we will have a reasonable body of work in the near future. So to summarize, these are the, we have seen that dust is almost ubiquitous. Wherever you see it, you will be able to see signatures of dust in the astrophysical context. To summarize very briefly, the cometary observations are an important tool to probe the early epoch of the solar system. And that comes partly because you have seen similar spectral features in cometary dust as you see in both young stars as well as in evolved and mass-losing stars. Okay, and mass loss even at the early stages in the red giant branch is a significant source of interstellar dust. And one can, of course, study the extinction in the plane of the galaxy and map it using the red giants, and also use the red trump stars as distance tracers, which we did in the case of LL45. And lastly, of course, magnetic field in the dark clouds can be probed by polarization, both in the optical as well as in the infrared. Infrared helps to go further into the core of the cloud compared to optical bands. And I will just conclude with a last view of one of the several manifestations of dust in our as seen from our observatory. Of course, going from the closest point, this is dust from the Thar Desert, scattering light from the region below. Luckily, it is all trapped below the boundary layer during winter, and so you can actually see the zodiacal light in this region. And there's a meteor here, and then, of course, a comet. And yeah, there must be many stars here with a mass losing, so you will have some dust there also. So I'll stop here and take questions.
Thank you, Dr. Sasikaran Ganesh, for the very nice and informative talk. So now the participants, this is our discussion and questioning time. So whoever having questions, you can please come forward and ask the questions directly, or for those having audio problems, you can just type your questions there in the chat section. Yes, questions please. Yes, participants. Any question? So, sir, in the chat section, question is coming up, sir.
Okay.
How magnetic field in the dark cloud can be probed by polarization?
Okay. Okay. So actually, the magnetic field vectors they have a polarization dependence, and Chandrasekhar and Fermi in a paper in 1953, followed by Oestreicher in 2001, and a few more papers in recent times have reviewed methods to use the dispersion in the orientation of polarization to come up with the polarization measurement. So the more aligned that the stars have their magnetic field, the polarization vectors would be more aligned with those. And then the smaller the dispersion, the higher is the magnetic field. Typically in molecular clouds in our galaxy, we see values ranging from 20 to 200 microgauss.
Yes, any other question?
Dear Shanrita.
Yes.
Yeah, I specifically do not have a question, but really I learned many things. Thank you, Professor
Yes,
Shashi Kiran.
please.
Yeah, no, but I would like to thank Professor Shashi Kiran. Many things, many concepts got cleared.
Okay,
yeah,
thank
so
you.
thank you for the nice talk, sir.
Thank you.
Yes, sir, I have one question.
Mm-hmm.
This nucleus of the comet,
Mm-hmm.
so when it is very near to the sun,
Yes.
on the average, the maximum temperature it can go up. How much it is, sir?
Oh, okay. So actually, when it comes extremely close to the sun, like the sun grazing comets, for example, they completely evaporate when they come very close. So those don't survive at all because the corona, they come close to the corona, and there the kinetic temperatures are on the order of 1,000,000 degrees, right? So it won't survive there at all. And
So Yeah, when it comes to million degrees, it doesn't survive.
Yeah.
So there
it's
is no
becoming like
chance that yeah. So there is no chance that other high energy phenomena can occur.
no, but on the other hand, there have been X-rays detected from comets, which was
Hmm.
a very big surprise when they saw this for the first time with comet Hyakutake and later on with several comets. So with the Rosette Observatory, they saw that the strong X-ray emission coming from comets which were within 1 AU of the sun. Okay.
Yeah, that's what.
Yeah.
Is there any? Yeah, is there any probability that X-rays can be emitted from there?
Yeah, so at that time, what it turns out is that there is a energy exchange interaction between the cometary ions and the solar wind particles. Okay, so charge
Yes.
exchange happens, and then that process leads to X-ray emission, and this traces well the hydrogen coma of the comet. So, which is much further out from the optically visible coma. Okay. So it can range to millions of kilometers. So in fact, some of these observations have been done when the comet is within 1 AU of the sun.
Okay, sir. Thank you.
Okay.
So,
Shashi, I'm Ashok Sen.
Yeah.
I have a question. Yeah. See, you commented about the Gaia distance.
About
The
the
distance of certain Gaia distance.
yes,
Distance
yes,
determined by Gaia.
yeah,
So, if I remember, you said beyond some distance range, the
yeah.
distance is not to be trusted.
It's yes.
So, is it
Mhm.
that, yeah. So my question is that for a given value of the Gaia distance, we
Mhm.
have asymmetric error bars.
Yes, yes,
If I remember correctly, I mean
yeah.
the lower side and the higher side.
Right,
I
right.
mean plus minus errors are not same. Yeah.
Yes.
So is there some sharp cutoff, or you want to say that as the distance increases, the error bar keeps increasing,
Yeah,
and on the
actually,
higher side it increases more?
right.
Yeah.
Yeah,
This
actually,
is my
what,
question. Yeah.
right. Yeah, it's an important thing which we found recently. So, what happens is that since this is optical wavelength, the Gaia mission is at optical wavelengths. So, the parallax measurements are not very reliable for the very faint Gaia sources. And when we compare them with, for example, stars which can be defined as red clump stars, we are finding some discrepancies. This is still work in progress, but in principle, the reason is easy to understand. The thing is that they have used a model of the galaxy to get the Bayesian as a prior for the Bayesian distance estimator. So that prior, if it is wrong, then you will end up getting a wrong measurement for the distance. So that is the reason that you have this problem. So the what is important is there to see the um, 1 by parallax distance, that if it is having a reasonable flag, then probably it is okay. It's up to about 3.5 kiloparsec. We can see that it matches reasonably well. But beyond that, the distances are measured using this Bayesian estimators. And there, if your priors are not properly chosen, you may end up getting improper numbers. So what I guess is that if you're looking at a region in a statistical manner, then maybe you can use the distances. But if you're looking at individual objects, then one has to be careful in using the distance blindly.
okay,
So
sir. One more
thank you.
question is there from the chat section.
Mhm.
So the question is, from the idea of Pennsperima theory, life on Earth did not originate on our planet, but was transported from somewhere else in the universe.
Right.
Out of my interest, maybe I would like to ask, did life on Earth start with the help from comet seeding? That's the question asked by Deepak Nath.
Okay. So actually, this is an important point, and there are no two answers, no agreeable um, answers to say of the points for and against both on this count. However, what is useful to keep in mind is that very complex molecules have been seen in not only in the interstellar medium but also on cometary bodies, and these molecules are precursors to even amino acids and further even more evolved organics. And some lab experiments in astrochemistry have been going on to try and replicate this kind of behavior, but really one doesn't know. Clearly, one thing which is of um, uh, in favor of life having originated elsewhere is that um, is that it would have had much further time, much more time to evolve to more complex molecules in the ISM than it would be possible on Earth, because Earth was not in a position to have such complex chemistry in the early phases. But clearly, this is a region where, I mean, this is a subject which is really beyond my expertise to answer in a more precise fashion, I guess.
Okay. So any other question? Any other question? Yeah, please. Yes, someone was asking something, right? So any other question? So if there is no other question, let's thank Dr. Sasikaran Ganesh once more. Thank you, sir, for the very nice talk. Thank you, sir.
It was a pleasure.
Over to you, sir.
Thank you, Okay, so thank you, Senorita Madam, for chairing this session. Now, next session will be chaired by Dr. Sasikaran Ganesh. So I request him to start that session.
Okay. Thank you, Madhuri. So in this session, we shall be having five talks. Is that right?
Oh, it is 4. He
four.
has again problem with the internet connection,
Okay.
So he could not present.
Okay.
So the same schedule. So 4 speakers are there.
Okay.
Yeah.
So the first talk is by Nilima Yasmin, who is from the University of Science and Technology, Meghalaya, India. And she'll be talking about possibility of light scattering tool to characterize biological particle in relevance to astrobiology. So Nilima, you have 10 minutes for presentation. I think we can probably squeeze a little more time. And of course, 5 to 10 minutes for questions. Yeah, your time starts. Take it from there.
Okay, thank you, sir.
Mm-hmm. Can you share your screen and hello?
Hello, sir.
Yeah, can you?
Am I audible?
Yes. Can you share your screen? We like to see the.
Yes, sir. I'm sharing now.
Yeah, okay.
Hello.
Yes.
Is it visible?
One moment. Not yet. No. You can click on the present now button and then choose. Yeah. Okay. I think it's coming up now. You have to choose one of the screens, I guess. Hello.
Hello.
Yeah.
Sir, is it visible?
No, no, not yet. Can you choose the screen? You have to pin the screen. That is what they're telling. Hello.
Hello. Sir, I'm sharing the screen, but it's not visible.
I think you have to select the screen which you want to share. So maybe what you can do is you share the whole screen and then go and change the tab to the presentation window. Hello.
Hello.
Yeah.
Sir, is
It's not.
that screen visible?
No, no, no. Actually, we are not able to see your screen. I think you have to pin the screen. If you go to the center, it will show. But then uh, when you select the screen, maybe what you can do is you can stop presenting and then yeah, present now. Click on present now, and then in that share the screen properly.
Okay.
Yes. Yeah. Now you select your background. You can click on the hide
Okay, sir.
button.
Is it visible, sir?
Yes. Click on the hide. You know, there is a small white bar which says you can click on
Yes,
hide
sir.
and then start it.
Okay.
Okay, good.
Okay, sir.
Good.
Good evening to everyone. I am Nilima Yasmin from University of Science and Technology, Meghalaya. So, my topic is possibility of light scattering tool to characterize biological particle in relevance to astrobiology. Now, what is scattering of light? Basically, we all know the phenomenon in which light rays get deviated from its straight path or striking an obstacle like dust or gas molecules. Not only this, almost every particle, the light is scattered by almost all objects in the universe. When a particle is illuminated by a beam of light with specified characteristics, the amount and angular distribution of the light scattered by the particle as well as the amount absorbed depends on the nature of the particle, that it is shape, size, and the refractive index of the particle. The technique of extracting information from objects by observing and analyzing the light that is scattered by the object is called the light scattering technique. Here you see, by using this technique, we can determine characteristics of particles in various scientific disciplines. As we know, all matter is composed of electric charge like electrons and protons. And we also know light is an electromagnetic wave. So when light encounters an obstacle or particle, electric charge in the particle are set into oscillatory motion by the electric field of the incident wave. Accelerated electric charge radiates electromagnetic energy in all directions.
Nilima,
And it
can
is
you perhaps move slightly away from the microphone? Thoda sa.
okay, sir.
Yeah.
And it is called radiation scattered by
Good.
particle. Now, scattering of
scattering by particles depends on the intensity of light and wavelength of light, scattering angle, particle size, and also refractive index. And particles information is obtained from the intensity of scattering pattern at various angles. Nowadays, light scattering is an important area of study and research. For example, astronomy, astrophysics, and also astrobiology deals with it. They deals with scattering in planetary atmosphere by and interplanetary dust also. People are also trying to find life in other planets or extraterrestrial spaces. Major topic of astrobiology, even NASA groups roadmap also on to understand the existence of life beyond Earth in the universe. How the terrestrial biosphere has co-evolved with Earth. All of us, as well as general public, also relate to these questions, to the search for life elsewhere in the universe. And this excitement leading us all to today's explorations. Therefore, it is not possible to get all the information of outer universe directly. So indirectly, I mean by light scattering modeling or by simulation, if we study biological particles or dust analog particles, after their characterization, we can assume the cases of presence of bacteria, virus, or any small particles in other planets. Indirectly, by this non-invasive method, without destroying the particle, we can collect information. Even in this present pandemic situation of coronavirus, we know it is very difficult to detect. We can study about this pathogenic spread in direct way by light scattering tools. Now, what the theory we use to characterize biological particles? There are many theories of light scattering. We consider the two theories basically, Mean scattering and T-matrix method, which is computer-based theory. As we already know that scattering particles have the ability to scatter the electromagnetic radiation in all possible directions. According to light scattering theory, Maxwell's equations are the most important theoretical analysis and computational methods for describing light scattering. An exact solution to these equations are only known for selected geometries of particles. All numerical techniques for computing electromagnetic scattering by non-spherical particles are divided into volume-based theories. There are different theories, many theories. Mean theory are applicable to particles have size comparable to the wavelength of light, proposed by Gostomi in 1908, and T-matrix method given by Waterman in 1971. This technique is for computing electromagnetic scattering by single homogeneous arbitrarily shaped particles based on Huygens principle. It depends only on composition, size, shape, and orientation. Combination of both experimental and theoretical approaches can lead to the better understanding. So, I'm not going to the details of the theory for time is short. So, Mueller matrix provide the complete description of the response of a medium to excitation by polarized light in either reflection or transmission configuration. The relation between incident and scattered Stokes parameters follows from the amplitude scattering matrix is shown here. And from in this matrix, we took the initiative to study the first two elements S11 and S12 for morphological characterization of a bacteria, Pseudomonas aeruginosa. The bacteria name is Pseudomonas aeruginosa. And we use the experimental setup. Here the two elements of the Mueller matrix S11 denotes the transformation of total intensity of incident light. Element is proportional to the phase function, provides information about the general signs, and S12 denotes the depolarization of linearly polarized light parallel and perpendicular to the scattering plane, dependent on size, shape, and complex refractive index of the scatterers. For an ensemble of particles illuminated by unpolarized light, the measurement of volume scattering functions, which is beta theta, which is equal to the first element of Mueller matrix S11, and the degree of linear polarization, which is equals to minus S12 by S11. And we use for this experiment the laser-based scattering setup, which is fabricated in Tezpur University by Dr. Sanchita Roy. We use this taking the experimental data by light scattering experiment for Pseudomonas aeruginosa bioparticles, which we had chosen for our scattering investigations, and highlighted the scattering profile for this sample. And the sample also prepared in the MBBT lab of Tezpur University. And this is the methods how the scattering setup detect the information about the sample. The measurements of the volume scattering function beta theta, which is equal to S11, and the degree of linear polarization p theta S minus S12 by S11 of bioparticles were carried out at 543.5 nanometer and 632.8 nanometer wavelengths. The scattering directions is fully described by the scattering angle theta and azimuthal angle phi. We presented the result obtained on averaging the azimuthal component phi. The graphs for volume scattering function beta theta and the degree of linear polarization are presented in logarithmic scale and normalized to 1 at 10 degrees. To give an indication of the shape of the aggregate, we provide a scanning electron microscope image. In the database, in this slide, for the sample, image made for the sample under studying during the light scattering measurement. The measured side distributions are also provided. Here you see the size distribution. Apart from shape and composition, size is a key property in determining the light scattering properties of small particles. Once it was measured and used in metheory and in T-matrix approach, a detailed description of measurements during the experiment performed under single scattering conditions. Therefore, we must have enough particles in the scattering volume to be representative for the ensembles of randomly oriented particles under study, but not so many that multiple scattering might play a role. It is important to remark that the measured values are normalized. Here you see the data analysis for Pseudomonas aeruginosa, and this is the experimental data, and this is the size distribution curve, which is a Gaussian curve, and particle radius is in micrometer 3.8, and particle size distribution is Gaussian distribution, and the refractive index for this Pseudomonas aeruginosa bacteria, we take the real part 1.3822 1.348, and the imaginary part is 0.
Nilima, how many slides do you have? Because we should conclude soon.
So I have 6 or 7 slides.
Oh, no, you'll have to conclude quickly because you already
Okay,
used
sir. Okay, I'm
15 minutes.
trying to.
Yeah, maybe we can come
Shortly.
to the results quickly. Huh?
Okay, sir. The measurement of volume scattering function and the degree of linear polarization at different azimuthal angle for beta theta is shown here. At both wavelength, 543.5 nanometer and 632.8 nanometer wavelength, the scattering direction is fully described by the scattering angle theta and azimuthal angle phi. We present the result obtained by averaging the azimuthal component phi. The graphs for volume scattering function and degree of linear polarization presented in logarithmic scale. Here, the measurement for the size distribution function beta theta in this graph, experimental and theoretical volume scattering function beta theta for Pseudomonas aerogenesis at different azimuthal angle. This plot shows considerable agreement with both the theoretical plots of me theory and T-matrix approach for both the wavelength, but showing inflections at some of the scattering angle. Here you see these discrepancies observed throughout the angular range for both the wavelengths due to size distribution of the assemblage of randomly oriented sample of Pseudomonas aeruginosa. Those may align within the sample due to environment alteration. Soft increase of beta theta presented at a scattering angle theta equal to at 100 degree onwards, with the theoretical plots at 543.5 nanometer, while beta theta at 632.8 nanometer shows slightly lower trends from 10 degree to 55 degree. An experimental average of beta theta also taken, and in these two plots, the first experimental average plot is closer to the me plot than T-matrix plot, and the second average experimental plot shows closer to T-matrix plot than me matrix plot. This fact demands a comparison with both the theories for the sample prepared in different concentration, and repeated experimentation with different sample concentration of the sample may allow us to quantify our result and provides us a better clue to the source of theory used for
move to the conclusion, Nilima, because we are running short of time now. Yeah, can you move?
These are the plots with error bars, and these are the plots of linear polarization d theta for this bacteria. And now the result and discussion. Overall theoretical scattering profile for beta theta showed good agreement with the experimental result, but because of non-sphericity of the assemblage of bioparticle Pseudomonas aeruginosa assemble, all the experimental plots corresponding to different azimuthal angle considerably agree more likely with T-matrix approach. The remarkable deviation for both beta theta and p theta may be attributed to the reason that the theoretical results based only one single dominant size of the assemblage, but in real sample there was distribution of sizes in case of beta theta. So our comparative analysis indicates that significant measurement of the scattering matrix element S11 and S12 related functions beta theta and p theta gives definiteness of scattering profiles of such systems. And this technique is a powerful diagnostic tool to detect precisely structural changes occurring in bioparticles like bacteria or other small particles. So our finding is that here we only took the initiative to find first two elements only. Other will also be studied later to get the complete morphology, so that we can provide the complete morphology for this species of pathogenic bacteria, Pseudomonas aeruginosa.
Okay. Thank you, Nilima.
Okay,
Yeah. Can you, so we have time for one or two quick questions or comments. So anyone want to take it up?
Hello, Nilima. Can you
okay,
move?
sir. Hello.
Can you move to that particular slide where you have been showing those variations of T matrix and theory for the phase functions? Can you move to that particular slide? Yeah.
Is it this slide?
Yeah, over here. It's okay. How you are configuring the composition of the particles that you are considering over here, or what kind of composition you are considering?
Hello. So can you
Uh,
repeat your question?
what are the refractive indices or the dielectric constants that you are considering over here?
Sir, refractive index we considering 1.348 to 1.348, 348.
348.
Yes, sir.
Okay, and the power law size distribution index for the base fitting you are getting at, means how you are varying the particle size distribution.
If what I understood is, I think she is considering the bacterium itself. So,
Yes, sir.
so then that would be as a constant size, or typically they have a fixed size. I don't know. Okay, but we should be going ahead. Nilima, there is one quick question here. Won't it be more apt to apply this tool to analyze possible biomolecules such as amino acids or glycoproteins in interstellar dust rather than using a somewhat more complex life system like bacteria? Is it clear? I mean, could you understand?
Sir, can you repeat the question?
Okay. So Akanksha is asking whether it is not better to use this tool to analyze biomolecules such as amino acids or glycoproteins in interstellar dust rather than using a somewhat more complex life system like bacteria.
No, sir. It can also be used to characterize amino acids, glycoproteins, and interstellar dust also.
Yeah, but from what I understood, you have done this on actual live bacteria, right? This basal scattering.
Yes, sir.
Okay. All right. I think so that way it's not exactly a theoretical study, but experimental plus theoretical, right?
Yes, yes, sir.
Okay. Okay.
Experimental
All right.
also.
So perhaps I think we should move on to the next speaker now. And
Okay.
so thank you, Nilima, and you can stop your
Thank you also.
sharing.
Thank you everyone for giving me such an opportunity.
Okay.
Thank you, sir.
So the next speaker in this session is Pramila Biswas from the University of Burdwan, West Bengal, India. She'll be talking about Chaplygin gas-type dark energy interacting with pressureless dust, thermodynamic study of the cosmos. Are you available online, Pramila?
Sir, I tried to contact her. She said she is having some internet issues there in her place.
Okay.
So
So
possibly,
should we
sir, you will have to move to next speaker.
Okay. All right. Maybe you can try and contact her in the meantime.
Yes, I'll inform you.
Okay. Thank you. So the next speaker is Debabrata Adak from Ayuka, Pune. And we'll be talking about dust polarization modeling at large scale over the northern galactic cap using EBHIS and Planck data. So Debabrata, is you online?
Hi, am I audible?
Yes.
So Nilima, can you stop your sharing?
Yeah, she is.
Thank you.
Yeah. Hello, Debabrata.
Sorry.
Yeah.
So how to share?
You click on the present now button down below.
Yes, present now button.
Yeah. And
Now
then to select the whole screen.
Entire screen. Okay.
Entire screen, and then select your presentation.
So it's not showing the presentation. Okay. Now can you see?
Yeah.
Okay. Thank you.
Okay. Now you can make it. Okay. Perfect.
So okay. So is it moving now?
Yes.
Slides moving?
Yeah.
Okay. Thank you.
So should I warn you at around 10 minutes?
12 minutes probably.
12 minutes. Okay.
Thank you.
Okay.
Hello everybody. I am Debabrata Adak from Ayuka. Thank you to the organizer for giving me the opportunity to deliver my talk in front of such wonderful audience. So this work has been done in collaboration with these people. So far the people have been talking about the astrophysical aspects of the dust. I'll be talking about slightly different topic, the foreground contribution of the dust in observation of the cosmic microwave background. So this is the cosmic timeline. When the universe was only 400,000 years old from the Big Bang, the hot plasma gets cooled down into 3000 Kelvin and start to get neutralized. And the relic photon trapped inside this hot plasma start free streaming. This relic photon travels all the way from the 1100 shift up to today, or the redshift 0, and we can observe those photons in microwave band using the 3 generation of the space satellites, Kobe, WMAP, and Planck. Since last few decades, we have been producing this wonderful CMB sky, However, the CMB is not completely unpolarized. At the end of the recombination epoch, or at the end of the last scattering surface, because of the quadrupolar asymmetry in the photon bath, when the photon gets scattered by the electron, they get linearly polarized along the colder axis. We all know, we observe this kind of polarization, linear polarization, using the Stokes IQU parameter, and this QU parameter is the spin 2 field. For the convenience, we go from spin 2 field to spin 0 field, and we decompose this QU map into the E mode and B mode polarization map. It's been well studied in literature that E mode polarization is generated from the density perturbations, and the B mode polarization is generated from 2 sources, either from the gravitational wave generated during the inflation, or the E mode polarization leaked into the B mode polarization when they travel through the large scale structure because of the weak lensing. Using the Planck satellite, we have observed the E mode polarization. So this is the power spectrum of the E mode and B mode. This blue line is the E mode power spectrum, and this is the power spectrum of the B mode this map. And this is parameterized by the tensor to scalar ratio R, and its amplitude depends on how much perturbation had been created during the epoch of inflation. So that's why this B mode signal is very important, and this is the main goal in the coming decades to detect. However, the real sky doesn't look like these maps. So they look like this. This is the 9 full sky observation at 9 frequencies by the Planck satellite. So you can see, so there is CMB at the low frequency, which is visibly prominent, but still contaminated by the dust. As you go to the higher frequencies, you cannot see the CMB because mostly they are contaminated fully by the dust. So that's why you understand how the dust is important in the context of the CMB physics. However, the dust is not unpolarized. The dust grains are the spherical in nature, and that's why they are dipolar, and they align themselves in the magnetic field. And when the starlight the light, unpolarized light from the stars travel through the dusty medium, they absorb the unpolarized light in optical band and emits the light along the longer axis in submillimeter or the microwave band. Microwave band. So that's why this dust is the polarized in microwave or the submillimeter bands. Then still question remains in presence of the dust, how we can see this faint B mode source, B mode polarization. So there can be two options. Either we can look for the one sky patch where maybe the dust is not contaminating the CMB, but the Planck observation says even in the faintest sky region, the dust is way order of magnitude larger than the B mode polarization. So which has the upper limit given by the BICEP 2 or K collaboration. So there is no sky patch where we can find that CMB is clean from the dust, or there is no frequency band where the CMB is not getting contaminated by the dust. You can see, so at all frequencies, the dust B mode is way order of magnitude than the CMB B mode. And if you go to the Fourier space, by the way, so this is not the very conventional PK versus K plot, because in case of CMB, this is the full sky observation. That's why instead of working in the K mode, we work in the this L mode, which is inversely proportional to the angle between the two points over the sky. And you can see the dust is way order of magnitude larger than this tensor to scalar than this B mode, which is parameterized by here this R 10 to the power minus 3, 10 to the power minus 2, 10 to the power minus 1, like that. So we are convinced that there is no sky patch, neither there is any band where we can see the clean CMB. So we have to move forward with the polarized galactic foreground. So at this point we can ask few questions. Given the present technology, what level of B mode is possible to detect, and to claim the detection, and we need to disentangle this dust and the CMB, and what level of what accuracy level we have to achieve in this component separation technique. To answer all those questions, we have to build a very precise model of the dust. So what if we don't have a very precise model of the dust? There is one evidence. So these are the very proposed CMB mission for the next decades. So here the author is trying to reproduce the input tensor to scalar ratio R for the different CMB missions in presence of the dust. When they are using the correct dust model, you can see the recovered tensor to scalar ratio, this here in the black line, is exactly same as the input tensor to scalar ratio. But when they're using the incorrect dust model for all of the missions, they are getting biased almost 50%. So then in presence of the dust, sorry. If you use the incorrect dust model, then maybe you are interpreting the fake B mode signal. Then then we have to move forward to build this dust model. We can go ahead with the in two directions. Either we can build the model using the MHD, magnetic hydrodynamic simulations, or using the H1 dust model. So H1 is the 21 centimeter observations. So people use H1 because at high galactic latitude, dust and H1 are tightly correlated, and because the dust and gas are very well mixed at high galactic latitude. My talk is based on this kind of simulations. Before going into my modeling framework, let me explain what are the statistical properties of the dust so far have been observed using the Planck satellite. So Planck informed that the dust E and B mode power spectrum is the power law, and the power and the spectral index is almost constant over the sky. And most interestingly, which is the unique property of the dust, that the amplitude of the B mode and amplitude of the E mode ratio is almost 0.5, which is constant over the sky. Not only that, so there is a large spread of the polarization fraction, and it depends on the sky patch you are looking at. The column density of the H1 21 centimeter, and at low density regions, there is a large spread. At high column density region, that is a small spread. That is probably because we are seeing the multiple clouds along the line of sight, and where the magnetic field orientation are not same. So that's why we are seeing the depolarization effect. So to build the model, we have to describe all those statistical properties of the dust observed by the Planck so far. So in our modeling framework, we have used the dust as a proxy of the H1 column density as a proxy of the dust intensity, because at high galactic latitude, this dust intensity and column density of H1 column density is tightly correlated. This is the H1 column density map produced by H1-4Pi collaboration. For our work, we have concentrated only over the northern galactic cap, where this correlation holds good. And so this full column density we have broken into the three conventional ISM phases: cold, warm, and unstable neutral medium. So this center is the northern galactic pole, and this outer circle is the plus 30 degree latitude, and this is the 60 degree. So these are the orthographic projection. That's why it's looking like that. And these are the very conventional ISM phases at high galactic latitude. Now let's move forward. So the game we play here is the following. So we assign the H1 layers along line of sight. Here n is 3, and we choose a phenomenological magnetic field model which has two components. One is the ordered magnetic field and plus the turbulent magnetic field. And at each layer, using our modeling framework, we produce the Stokes IQE map. Then we co-add each layers to produce the observed sky, and to match them with the real data, we add some extra end-to-end noise realizations produced using the Planck simulations, and then we match the 1-point and 2-point correlation functions of the dust to tune our model parameter. So in our model, there is 7 parameters. I'll go one by one to tell you how we have fixed these 7 parameters. So this is the modeling framework we have used at 353 gigahertz. We have used the 353 Planck data because this is the most sensitive channel of the Planck. Let me explain the each term. This P0 is the intrinsic grain alignment that depends on the grain physics. So this is not well studied. So this is one free parameter in our model. And gamma is the projection angle of the 3D magnetic field over the 2D plane of the sky. And this is the line of sight, and perpendicular to this is the plane of the sky. Psi is the polarization angle, and epsilon is the emissivity, which translates the H1 column density to the dust intensity. However, sorry.
You may have to start concluding. Okay.
Okay. So, okay, so we have chosen the 16% of the sky where the model works. So in magnetic field model, we have the large scale magnetic field and the small scale. So FM is the amount of turbulence, and the direction has been generated from the power spectrum. So this is the direction of the magnetic field. You can see the large scale magnetic field follows the spiral arm. So this is the direction of the magnetic field, and this this butterfly pattern comes due to the small scale large scale magnetic field. And for small scale magnetic field, we have fixed the amount of turbulence present in each layers. So this FM is FM 0.5 and minus 2.4 is the turbulence and the slope of the of the magnetic field. Now let's match the data with the model. So this is the 1-point correlation function. This is the polarization fraction and polarization angle, which our model can describe the data very well. Now let's move to the polarized power spectrum. In case of power spectrum, if you match the slope and the amplitude ratio of the E and B, they are matching almost in 1 sigma accuracy. Now and also in intensity level, you can see the morphology of the intensity is matching with the data. And another property is the polarization angle dispersion, so which describes how well oriented the polarization angles are around your central pixels. And in 2015 paper, Planck has discovered that this dispersion functions and the polarization fraction are anti-correlated. Even that can be described using our model. That can be described using our model without tuning the out 7 parameters further. Now let me conclude. So the CMB B mode is very subdominant compared to the dust over the whole sky at all scale and at all frequencies, and it's very challenging task to detect the primordial B mode, which is the direct evidence of the inflationary era. And the statistical dust model is a very necessary step to claim the detection, and our model can describe or reproduce the all statistical properties of the dust so far has been informed from the Planck observations. And our model is doing well in that direction. So one little advertisement for the 4th generation CMB missions. CMB Bharat, the CMB Cosmology Consortium has submitted one proposal to ISRO. So this is in consideration phase, and this this mission is led by Professor Tarun Sauradeep. And thank you for your attention.
Okay, thanks, Devabrata. And we have time for a few questions.
Go ahead.
Comments. So anyone would like to ask anything specific?
Yes, I have a question.
Yes,
I'm Ashok Sen.
yes.
Hi.
Yeah, am I audible?
Yeah, sure.
Okay, see, what you said in the beginning, it is in the early phase, the electron and photon interaction, which gives rise to cosmic microwave background polarization. Am I correct?
So are you talking about
the B mode?
Yes.
Yeah, the B mode, yes.
Yes.
Now, yeah, I just want to know from you to what level of confidence this interaction has been modeled. Because dust polarization, for the people who are involved in galactic astronomy, we find dust polarization itself has a lot of uncertainty. They are direction dependent, they are wavelength dependent,
Correct.
And there are many other issues. The 3D dust model is also there.
Correct.
So, so to the other part, I mean this electron and photon interaction, how correctly it has been modeled?
How correctly
what extent
is saying whether there is a B mode signal or not?
Yes. When if it is dustless, if you do not have any foreground dust, then what you observe.
I'm getting it. So if the inflation is the correct model, then the gravitational wave has to be generated, and because of the gravitational wave, there will be a cross pattern in your cross and plus pattern in your photon density bath. And when the this kind of photon are getting scattered at the end of the recombination epoch, they will be linearly polarized, and this and this kind of this quadruple pattern should be generated if the inflation truly happens. Still, it's a phenomenological model. But if inflation is the true model, then there has to be gravitational wave which will produce the quadruple asymmetry, and that will give rise the B-mode polarization.
Okay.
Am I giving correct answer? Hello?
Yeah, I don't know if he's had some problem and logged off or.
Yeah, I think I have got your point, but yeah, he is back, so he can answer.
Okay. Okay. So.
Okay.
any other questions?
Yeah.
He
I
is
thank
back.
the speaker. It is okay. Yeah.
Yeah.
I thank the speaker. It is okay. Yeah.
Thank you.
Okay. Okay. So anyone else who would like to comment or question for Devabrata? If not, let us thank the speaker and then move to the next, I think probably the last talk of this session by Vipin Sharma. Vipin, are you here? So Vipin Sharma is from the...
Yes, I will speak. I am here.
Okay. Vipin Sharma is from the University of Lucknow, and he will be talking about astrophysical constraints of modified gravity theories in the dusty galactic halo. So Vipin, you have usual time of about 12 minutes plus a few for questions.
Okay.
You can start your presentation.
Okay. Okay. Okay, so here we will talk about the astrophysical constraints on the modified gravity theories in the dusty galactic halos. So let us begin with two important terms, topics, which here basically we will deal with modified gravity models. And so we take here FR and FRT. This is the main theme of our work. And we try to constrain the rotational velocity profiles in the dusty galactic halos, and which from observations, we suggest that there is a flat profile of the rotational velocities in the dusty galactic halos. So we will try to model out such flatness paradox in FR and FRT gravity theories. So this is the basic theme of our work. So let us start on the first slide. So this is the sorry. Okay. So this is the latest cosmic budget of energy densities of our universe, and from here we will clearly see that the dark energy is almost covers 70%, and dark matter is almost 27%. So we will try to model out the dark matter for dusty galactic halos, astrophysical dark matters. So this is the basic model of Einstein gravity theory, that is the lambda CDM model, which actually explains the dynamics of astrophysical bodies from local scale to cosmological scales, and hence it explains ultimately the dynamics of the universe, but with some exotic components. That is a big thing which we don't know now. So there is a long-standing problem in the modern astrophysics of non-Keplerian observational behavior of the galactic rotation curves. So these are basic the basics of about from how we trace the rotational velocity curves in the dusty galactic halos by a 21 centimeter radiation, which is actually the neutral hydrogen map from 21 centimeter. Okay, so these some observations suggest that the rotational velocities profile in the dusty galactic halos is approximately constant. Okay, and such observation in turn suggests that there must be a presence of pressureless and cold dark matter particles, and which can explain the flatness profile of the rotational curves beyond the optical radius, okay, in the dusty galactic halos. So there are various possible candidates of dark matter, which ranges from 10 to power 6 solar masses, astrophysical black holes to 10 to power minus 6 electron volt axions. Okay, so these are some basic things which traces the presence of dark matter. But still, we don't know. We don't reveal it. It's through various running experiments like Xenon, Gamma, Libra, and so on. Okay. So here we start to try to model out the flatness profile in modified gravity theories. So here we take FR, which is basically the modification of Ricci scalar curvature via treating Ricci scalar as some functional form of it. And in modified gravity model, we take the coupling between the geometry and the trace of the dust-like matter present in the universe. Okay. So here we deal with the power law profile. Here delta for FR model, we take r raised to the power some 1 plus delta, and for our FRT model, we try to constrain the parameter beta. Okay. So actually here delta and beta represents the deviation, how much deviation is required from the Einstein's theory in order to predict the flatness profile of rotation curves. So basically we try to constrain delta and beta here. So recently such models are also discussed in our papers presented in here. Okay, so let's start with the FR gravity model. The action of FR gravity theory is basically written as like this, and in FLRW background metric, the modified field equations is given by G mu is proportional to T mu some curvature in the absence of matter part, since we modified the gravity part only. And by modifying the gravity part, we try to trace the flatness profile. Okay. So this is our previous work. Here we draw the cosmological dynamics close to the galactic environment for dark matter explanation. So basically, which is the geometry is given by this: R is proportional to R naught H over H naught raised to the power 1 over 1 plus delta. R naught is the constant, present constant, and H naught is the present constant, and H is the Hubble parameter. Okay. Now the galactic geometry and tangential velocity profile in FR background. Okay, so the main motivation comes from this profile, from this geometry. R is equals to R naught. So, and the main motivation to investigate the dynamics close to the cosmic dynamics close to the galactic environment is actually comes from the Einstein Schwarzschild de Sitter space-time metric. So here we can see that the Newtonian potential, that is minus 2 gm by r, is coupled with the lambda. That is, here the two solutions are superposed. One is Newtonian potential and the other is the cosmic potential one. So these two solutions are cosmic Newtonian and cosmic. Local scale and cosmic scale are superposed via this metric. So this is the important feature of Schwarzschild-like space-time, as it reduces the Einstein's field equation, which are actually non-linear, to linear form in order to join different solutions. Otherwise, we cannot superpose different solutions of Einstein's field equations since it is non-linear. Okay, but metric provides us to join two cosmological solutions, two solutions, local and cosmological. So with this motivation, we develop the space-time metric is this, and obtain the effective radial equation for test mass in the galactic plane under the weak field limit. This places us like this. Here A double dot upon A basically A is the scale factor and T is the cosmic time. The solution of modified gravity is, as we know, is obtained in terms of scale factor, and for the proposed model, the solution is given by this. Okay, so we know A. So we from R effective equation, R double dot effective equation, we can get the rotational velocity profile via using the basic kinetic equation like this, given by this. So here we see that the velocity profile depends on the Newtonian part. The first term is Newtonian, and the other one is basically arises due to the space-time curvature, modification in the space-time curvature. Okay, so now 21 centimeter astronomy in dusty halo of typical galaxy and FR constraints. Okay, so in this slide here, we trace the velocity profile versus delta profile, right, far from the galactic disk. So basically, this figure shows the behavior of rotational velocity profile with the model parameter. As we see that for delta less than 0, small, the rotational velocity profile decreases. But on the other hand, if we see that delta, if we take delta as much less than 1, then what we see here, the rotational velocity profile becomes constant. Okay, so this is the behavior of velocity versus delta. Now with this, so actually this provides us the main motivation to take smaller values of delta on comparing these two curves, first figure 1 and figure 2. So that's why the smaller value of delta is preferred to trace the rotational velocity profile in the galactic halos. So here we take, as you see, 10 raised to the power minus 6 of the order of 10. Delta must be of the order of 10 to the power minus 6, right? Raised to the minus 6. Okay. So now with this value of delta, we try to constrain we try to figure out the rotational velocity profile of our Milky Way galaxy. So the black dots represents the observed data points, and for delta is equals to 10 raised to the power minus 6, we get the behavior of rotational velocity profile like this. Okay, so as we see, we are away from 15 kiloparsecs. So okay, so we try to trace out the rotational velocity profiles in the dark matter, in the dusty galactic halos, and which comes to be constant like this. Okay, so this is basically now. So actually here we constrain for delta is equal to 10 to the power minus raised to the power minus 6. We obtain the flatness profile in the dusty galactic halos. Now, okay. Now since after this we try to move on our next model, FRT model. Here, in this model, that R represents the Ricci scalar and T represents the trace of dust-like matter. We take the interaction coupling between these two terms and the coupling between and try to trace out that whether the coupling between these two terms can explain the flatness profile or not, and try to constrain the parameter beta. So the FRT action is given by this, and P is the trace of dust-like matter, which is given by this. LM is the Lagrangian density of matter. So the variation of the above action with respect to the metric tensor gives the following field equations. Where T mu, where the interaction terms, as you see here, that in the previous in FR gravity theory, we have T mu nu curvature terms. Here we have T mu nu interaction terms, interaction between the geometry and the energy momentum tensor. So here what we do, our present work, we take the Schwarzschild again. We try to find the solution of the FRT field equation in galactic astronomical background. So basically, the Schwarzschild like spacetime metric is preferred. So we take since we are dealing with power law model, so we write the Schwarzschild like static metric background as in power law form, and try to trace out try to figure out the components of the metric for this model, FRT model. Okay. So
can you start concluding?
Okay. So these are basically the field equations, and rho m is the normal density of matter, energy density of matter, and rho interaction is just arises because of T mu nu interaction term. Okay. So with this, following the approach by Weiss-Hobbetti to solve such nonlinear differential equation, we get the solutions. We get the components of our differential equation, like e raised to the power epsilon and f raised to the power epsilon. FRT model and dusty galactic halos. So this is actually basically the main point of work over here. Let's skip this. Okay, so for modeling the dusty galactic halos, we use, since in the dusty galactic halos the gas density is very low apart from the disk. So here we use rho m, that is the energy density of matter, is very much less than the energy density of interaction term in the dusty galactic halos. So the metric component, our metric component, reduces to this. And as per Newtonian gravity, we must have energy for Keplerian behavior. We must have rho proportional to r raised to the power minus 2. Okay, so motivated with this, we assume the energy density of matter is given by this, where in gamma raised to the, where gamma is greater than 2 for the astronomical dark matter explanation. Okay, so with this explanation, we obtain the components of the metric like this. The interaction energy became this. The 21 centimeter industrial halo with this, or we trace out the equation of test star in the r coordinate, and obtain the stable circular velocity. Okay, now the tangential velocity for the proposed model is given by this. Now, since in our previous work we obtained the constraint on delta is raised to the power 10 to the power minus 6, so with this, using this, we have gamma 1 plus beta is approximately equals to 2, and which reduces the interaction energy density is almost proportional to 10 r raised to the power minus 2. So the metric component reduces to a constant value for dark matter explanation in the galactic, for the galactic dark matter explanation. Okay, and the r component is this. R component is basically not constant. Okay, so for clearly we see here that for gamma is equals to 2, the GR gravity theory is recovered, and for gamma greater than 2, we are in modified gravity theory. And basically for gamma is equals to 4, we get beta is equal to itna, and this constraint value follows the Bianchi conservation principle. Okay, so conclusion, let us conclude our work. So basically we try to model out the dark matter halos in FR and FRT gravity theory, which we investigate the switching action of the raised power from R to T and obtain the constraints on delta and beta via 21 centimeter emission, and which is proved from the Cassini space probe. Our constraint value is proved from the Cassini space probe data. Okay. So with this, we have presented some basic theoretical ideas which together with the virial theorem are necessary tools for comparison of the prediction of the modified gravity theory theoretical model with the astronomical observational results. Okay, so these are some references which you have used. So thank you.
Okay, thank you, Vipin. So questions for Vipin? Can have a few questions.
Can you please go to page number 14?
Okay.
Slide number 14, 14.
Okay. Yes.
Yeah, I want to ask a few things about the observational data, related to observational data. Where from you have collected this observational data?
Sorry. Here we try to, here I don't mention the references, but we are to from actually the references are mentioned in our paper, our paper which is mentioned in reference, references, first reference. Okay, so
yeah.
Okay,
Again,
so
please go to that
find
page. Please go to that page.
Okay.
No, actually, what is my comment? Reference should be there. Otherwise, it is totally confusing, right? Otherwise, how people will believe. So, what is the amount of error in this observation? It is not mentioned there.
Sorry?
What is the amount of error? Error associated with this data point. Error.
Oh, okay.
Error.
Okay.
Yeah.
So,
what is the amount of error associated with this data point? Otherwise, you see, you have fitted that curve, but there is no error plotted. Without error, I think it will be difficult, right?
Right.
Yeah. Please take care of that.
Okay.
Yes. I have no other comment. Thank you very much.
Okay.
Yes.
There is one question in the okay. So there is a question by Usman Sarki. Maybe okay. He says, have actually enjoyed the presentation by Vipin. What is the significance of metric tensors in the study of dust and astrophysics?
Okay. What is the significance? Can you repeat the question once again?
So his question is, what is the significance of metric tensors in the study of dust and astrophysics? So I think he is wanting to know how you used tensor geometry in this in the purpose of understanding dust related questions. Probably.
Okay. Since just a second. Okay, so here we obtain our field equation in metric tensor. That is for FR and FRT gravity theory. We take the action to be depends on metric tensor G mu nu only, and here.
Whenever you try to write down the equation in explicit form, you have to assume the space-time metric, right? Once you do that, you have to,
Okay.
I will think about that. Okay.
Okay, yeah. Yeah, probably this point which you have on the screen right now, where the observations of rotation curves in dusty galaxy halos instead of considering dark matter. I don't know. We have to think about that in more detail. So any other questions or comments? Vipin? Otherwise, anyway, I think we don't have the last speaker, so we can take one question. Otherwise, we can conclude the session if there are no further questions. Okay, so I don't see any further questions in the chat or online. So thank you, Vipin, for this interesting perspective, and all the best for your future work. And with that, with that, we come to the end of this session because we are not able to contact the last speaker of this session. And so we conclude the session here, and I hand over the chair to the organizers for the valedictory function. Thank you.
Yeah, so I thank Dr. Shashikiran Ganesh. Yeah, so Gulabsha, I was just giving to you. So I would like to thank Dr. Shashikiran Ganesh for organizing this session and chairing this session. It was really a nice session, and I also welcome all the speakers on behalf of the organizing committee. The next program will be valedictory session. So over to Gulabsha.
Thank you so much, sir. So we have come to the end of this 2 days international conference on dust in astrophysics. So we'll have a short valedictory session now, and before that I will be sharing the feedback link. So I request all the participants to please fill up the form and submit within time. So we are going to start the valedictory session. I request our HOD ma'am, Professor Otri Deshamukho, to please chair the session. Ma'am, please, over to you.
A very good evening to you all. Gulabsha, somebody is asking for the link again. You can please send it. And
Yes,
yeah, so the 2 days have passed. So first, and we are at the end part of the yesterday morning we started, and now we are at the end point. I really enjoyed the last session because it was more appealing to me. All the sessions are good. I personally learned many things. And now actually I have no words to thank the speakers because they have spent quite a good amount of time, sparing time from their valuable schedule. So it's and the participants, so without whom we could not have organized such a program. I would like to thank Dr. Himadri in spite of his not being well that way. He has organized such a big program, and also Gulabsha for handling everything. So before as we start, Professor Ganesh is there with us, or he has left? Hello.
Hello. Yes.
Yeah, you are there, sir.
Yeah,
So, yeah, I would like to hear from you how you have liked this. I mean, what is your feeling about the whole episode?
Yeah, I think it was very good 2 days and a very useful session for all the participants. Unfortunately, I could not attend some of the sessions. We had some connectivity problem in the morning with the power. But I really enjoyed whatever talks I could listen to. And I think it was a good opportunity for the youngsters also to present their work and learn from each other. So it's especially commendable that such an effort was made and successfully executed by the organizers, and really all congratulations to them from my side. Thank you.
Sir. So actually, it's a nice opportunity that this web platform. This is a better side. I mean, good side of COVID, that we have been exposed to this online platform. Now it's very easy one way to convene such meetings. With people need not move out of their own place, and then connectivity is an issue. I do agree, but then also if you compare it with the hassle of the hard meeting, it's a bit less. Obviously, the front-to-front interaction has some other meaning, but there also it's a good opportunity for all of us to get a platform to interact. People from similar working area interacting with each other, learning new things, and now you can contact with each other over. I mean, you have contact addresses possibly, or the organizers can supply you if you want to discuss with some particular resource person or some particular presenter. So that is possible. We have with us Professor Ashok Kumar Sen, who is the senior most one in the department. And since the inception of astrophysics in the department, sir is there. And this event, we are actually celebrating the silver jubilee of the department. So it's a part of that celebration. So, sir, I would like to hear from you. Everyone else will be happy to hear from you in this occasion.
Yes, it was wonderful. I really enjoyed it. Yesterday, I had some connectivity problem. Otherwise, whatever talks I have attended, I really liked it. And I thank all the invited speakers from outside India, Professor Zupko and Katerina. I think she is here now. And I also thank other participants who had presented their work. Quite a good number of them are PhD scholars, students from faculties also. And as you have told, it is a part of our Silver Jubilee celebration. We have completed 25 years in Assam University, Silchar. And I thank all of you for organizing this meeting. Thank you.
Thank you, sir. I would like to invite now the participants to speak your experience in the event. Anyone? I mean, not one, maybe two, but please unmute yourself and speak. Participants?
Yeah, good evening, ma'am.
Yes, yes, Deepak, please.
Yeah, good evening, ma'am. And good evening to all. It is very fascinating and very engaging 2 days. Indulge me or allow me for 3 minutes to speak. First of all, I would like to share with you that I was a student of this department for the period 1998 to 2000. And presently, I am working as an assistant professor in the Department of Physics in a government college, Nagaland. Now, hearing the voice of Professor Ashok Kumar Sen, who was our teacher then, I'm really happy. Sir, I wish you a happy and sound, healthy life, sir. I, on my own behalf and on the behalf of all the participants, would like to convey a very hearty thanks to all the speakers for sharing your important findings, ideas, and thought with us. We have learned many things about comments, particularly polarization of comment, morphology of cosmic dust particles, and so on. I also like to congratulate the conference team leading by Dr. Himadri Shekhar Das. This international conference for the 2 days was extremely fantastic in terms of talk as well as in terms of technical support. Time management was very outstanding, madam. Really, we are really touched with this conference. I wish that Physics Department of Assam University would conduct such more conference in the days to come. Last but not least, I think organizing committee for giving us such wonderful platform to accelerate our knowledge in the line of comet. Thank you, ma'am. Thank you. Allow me to speak on behalf of the participants.
Thank you very much, Deepak. I would like to share one information with the participants. We have a YouTube channel of the Department of Physics, Assam University, Silchar. If you type that in YouTube, you will get to the channel. We are trying to put all the videos of all the programs we are organizing this year as a celebration, as a part of celebration of Silver Jubilee. I would request you to subscribe to that channel so that whenever we are organizing something, you can be a part of it if you are interested. Anyone else wants to speak?
Madam, you can read out a message from one of our invited speaker, Ekaterina Chornaya.
Yeah.
In the chat box.
Sent a message. Very nice, Himadri, for pointing out. So she said that she is not being able to speak in the microphone. She is telling that it was a great conference. All the reports were excellent. I really liked it. I hope that the authors I can meet at other events. It was very nice to meet everyone. Thanks especially to Dr. Himadri and the committee for inviting me. Thank you, ma'am, for joining us, for spending your time to talk to the participants, because this is mainly an interaction event, conferences. So it's not one-way traffic. So I thank you very much, Ekaterina. So anyone else who wants to share?
Bimanda is there. I can see.
Yeah. After
so
a
we can request Bimanda.
Yeah, sure. Hello, Dr. Bimanjati?
Yes. Can you hear me?
Yes, sir.
Yes. Yeah. First of all, I would like to congratulate Assam University Physics Department of Physics, Assam University, for organizing such a nice workshop, International Conference of Dust in Astrophysics. And I would like to thank you people for inviting me to take a part in that conference. I have really enjoyed, but due to some reason, I cannot. It was not possible for me to attend all the sessions. I have missed actually 2 sessions due to some of my urgent work. But I think it is a nice workshop. Uh, Whatever we have in our mind before organizing this kind of workshop, I think it is 100% successful. And I want to mention one point: time management is extremely good. Time management is extremely good, and I think we can exchange our knowledge uh, in this conference to our upcoming generation. I think it will be a very helpful for them as well as for us. Thank you very much.
Thank you, ma'am. Thank you for the organizing committee for sparing so much of your time, spending with us, spending with the participants. Yeah, I have a comment, another comment. Anil, the Akansha Mahabatra says that really illuminating and insightful studies by so many researchers. A big thanks to the university organizers for such an event. Understanding dust in astrophysics gave me a broad approach in my quest of astrobiology. Okay. And then Kuldeep Rana says, very nice conference. Anil Das says, great international conference on dust in astrophysics by Assam University researcher. Musa Usman Sarki tells that it's very interesting being part of this educative and enlightening program of ICDA 2020, joining you online from Nigeria. My special appreciation for the organizers, especially to Dr. Himadri Shekhar Dash for his kindness. So it's nice, Musa, to hear from you all. I thank all of you, actually, Anil, Akanksha, Kuldeep, for sharing your views. Anyone else who wants to speak? Or otherwise, I would. Yeah, sure.
I'm Tanvir Hussain.
Yes, please.
First of all, congratulations to the Department of Physics, Assam University, for 25 years. And it was a very wonderful 2-day e-conference with a lot of good and insightful talks on dust. Given that I am very, very interested in understanding the comets, and also it was very insightful. So thanks to all the speakers. Thank you to Dr. Himadri sir for giving me an opportunity to attend this conference, and everybody involved. So it was all over a very good conference. And as Dr. Biman sir said, that it was very well managed. The time management was very, very nice. So thank you and all the best.
Welcome, Dr. Tanvir. Anyone else who wants to share their view? Ravindra Mahato says, extremely enlightened by hearing such nice papers, and congratulations, Department of Physics, Assam University, for conducting the conference as efficiently as ever. Nilima Yasmin says, thank you all for giving such an opportunity. It was very much informative and fascinating sessions. A lot of thanks to Assam University. And then Sharwani Patnaik says, astrophysics isn't popular in my city yet, but seeing such enthusiasm here made me really happy. And I am looking forward for such interactions in future. My dream always has been to look up in stars. And here I was able to perceive more than just a vision. Thank you so much. Thank you, Sharwani, for sharing your experience. Thank you, Ravindra. Thank you, Nilima. Anyone else who wants to? Yeah. So Professor Shen says, let us thank Dr. Biman and Dr. Ganesh. He wants to share this with the audience. Anyone else who wants to share? Or otherwise, I will request Dr. Himadri, the convener of the program. Yeah. Anyone else? Hello. Yeah. Dr. Himadri. Hello. Am I audible?
Yes, yes.
Yeah. Can you please share? I mean, you also share 2 words here, please.
Yes. So I'll be with the participants for last 2 days, and I talked too much because of many issues. So I want to thank all the participants for joining in this session, and I could see that always the participants' numbers were constant, and it actually proves that the talks were really interesting. We initially, when we approached to Dr. Jupko, and initially I talked to Jupko, and then he gave his positive response. Then his student Ecterenia actually ready to deliver a speech. Then we had made a comment, and already I talked with Dr. Ganesh and Dr. Medhi regarding this, because our aim is to actually conduct a conference on dust in astrophysics, and 4 speakers, invited speakers, are expert in this field, and various aspects of cosmic dust particles, then polarimetry, photometry, all are discussed in this meeting, and it is really a very good meeting. Organizing a web conference nowadays is very difficult because of the internet connection. So I'm very lucky that actually I conducted this total system from my home, and I should thank to the network that it worked well. It never got disconnected from my laptop, because recording was done by my laptop, and any case it was not happened. And as Atri madam told, that all the talks and lectures will be uploaded in the official YouTube page. I request all, after 2 or 3 days, this videos will be available in the website. So if you need any further information, you can contact with us or can download the video from the YouTube. Another point is that based on the feedback and other things, we are preparing certificates. So it may take some 7 days or 8 days time. So please give us time. Immediately we cannot actually give you the certificate, because we are preparing the certificates, and it is a tedious job, you know. So you should not expect that you will get the certificate by tomorrow, but we will try our level best to send you certificates as soon as possible. And last but not the least, I would again want to thank the university authority for allowing us to conduct this conference, and also to our head of the department, Professor Otri Deshmukh. Because of her, actually we had to organize this conference in the month of July. Yes, she actually first came to me and told me, Himadri, why don't you organize conference. She is always talk like that. She wants to organize many programs in the department. And for last 1.5 months, we organized around 4 to 5 programs in our department. So she told me that, then I told her that it is too early, because if you want to conduct an international conference, it takes some time to contact with all people. And since DAST group is not so much strong in India, so we need to get the contact of all the participants. But luckily, within 10 days, it is possible for us to conduct the conference. And another point is that nowadays, almost every day, different departments of our university is organizing many conferences. So for us also, it is very difficult to get all the people to be involved in that particular conference. So anyway, we managed it, and credit should goes to our head of the department. And that's all from my end, madam. Thank you very much.
Thank you very much, Himadri. Yuva Inusa says that I commend the organizers for this conference. A job well done. So it's very nice to hear from you all. And as Dr. Himadri already shared that, yeah, that time when I approached him, there was a guest comet in the sky. So I was trying to tap that event. And then in hurry, it was not possible to organize this conference. So we just organized a popular talk that will also be uploaded in our YouTube channel. And moreover, we have live programs also from time to time. So you can keep an eye. I won't extend much because of this connectivity problem. Since morning, I'm there sitting in the department, because otherwise, if I go home, I am not sure about the connectivity. So thank you very much. I think, Himadri, we can end it here.
Yes, yes.
Anything, any formality left?
I don't think anything is left.
Okay. So on behalf of the organizers, I would like to thank one and all involved for all their kind helping hand for making this event a successful one. Thank you all one again. I don't want to take the names because I may miss someone. Everyone who has, helped us in organizing this event in any way, I would like to thank them all on behalf of the organizers. Thank you all. Thank you. Bye-bye.